Coming back to rational functions, we're going to focus on rational inequalities this time. From section 3.6, that second part, we did polynomial inequalities already. Now that you know all about rational functions, we're going to think about where those graphs will be above or below the x-axis or on the x-axis. Now, when we did polynomial inequalities and did that test point method, we had more bullet points over here, more steps, but you already know how to do the test point method. So really, we only need to focus on what things are a little bit different when we're dealing with rational inequalities instead of polynomial inequalities. All right, so when we are trying to solve inequalities for rational functions, we have to first, just like with polynomials, rewrite the inequality so that it's set to 0. So 0 is on one side, and a ratio in lowest terms is on the other. This bit's a little bit different because we didn't have ratios with polynomial inequalities. So we've got it set to 0 with just one ratio in lowest terms on the other side. Second step, we need to find all the zeros in both the numerator and the denominator. Those zeros, whether they're in the numerator or denominator, it makes a difference. If you have zeros in the denominator, that's places where our function is undefined. That gives us vertical asymptotes or holes in the graph. When you have zeros from the numerator, zero in the numerator represents actual function values. So where my y value is equal to 0, we have a 0 in our numerator. Zeros from the denominator are never included in our answer. Zeros from the numerator could be included in our answer if our inequality symbol says or equal to, like this one does. The third step is to place all zeros on your number line. Those are our boundary points. And then pick a test point inside each of the intervals. Okay. So we're going to find the intervals that satisfy this inequality. It's already set to 0. We already have a single rational expression over here. We can make sure it's in lowest terms. I'm going to go ahead and factor that denominator. So my denominator, x squared minus 1, that's difference of squares. That's going to factor out to be x plus 1, x minus 1. Nothing cancels. Okay, so we've got our inequality written with 0 on one side. We know it's in lowest terms. We have found all the zeros. We have 2 zeros from our denominator. We're going to have 1 0 from our numerator. We need to place those as boundary points on a number line. So our denominator, I have x equals -1 and +1. Since they come from the denominator, they're places where our function is undefined. From our numerator, we would have x equals -3, and that is a function value where y is 0. So I need to put -1, +1, and -3 all in order on my number line, least to greatest. So -3, -1, +1. I have 3 boundary points. That means I have 1, 2, 3, 4 intervals I need to check. -3 comes from the numerator, so it's a function value of 0. I'm going to mark that so I remember. -1 and +1 come from my denominator, so they're places where my function is undefined, so they can never be included in an answer. Now I need to check test points. So I need to pick a test point in each of my intervals. I've got 4 intervals, so I'm going to do 4 test points. As x gets large, I can do -100 and +100 here at the end. 0 sits between -1 and 1. The easy integer between -1 and -3, I'll test -2 there. So those are the values I'm going to test. if x equals negative 100, what happens? Well, right here, negative 103 is a negative 97. Negative 100 times a negative 100, that's huge, it's positive. It doesn't matter if I subtract 1. 100 times 100, 1 with 4 zeros, so 10,000 minus 1. Basically, what I'm interested in here is I have negative divided by a positive. Negative divided by a positive is negative, so everything in this interval is negative. What if x is negative 2? Well, negative 2 and 3, that's positive 1. Negative 2 times negative 2 is 4. 4 minus 1 is 3, and that's positive. So everything in this interval is positive. One main difference between our polynomial inequalities and our rational inequalities, we can reason through our polynomial inequalities and get a really good visual idea of what the graph would look like. Rational inequalities, it takes longer to graph than it does to do the test point method, so we tend to do the test point method a lot more. Alright, so for this third interval, if x is 0, I would have 3 over negative 1, which is negative, so everything in that interval is negative. If x is positive large number, 100 is easy, that would be 103 over 10,000 minus 1 again, so that's a positive value. So positive over positive, that's what I'm interested in, positive over positive, so everything in this interval is positive. Now to answer the question is, where is this polynomial function greater than or equal to 0? So where would the graph be, above the x-axis or on the x-axis with a value of 0? Well, positive greater than 0, that's these two intervals. So my boundary points here I've got between negative 3 and negative 1. And then I've also got this upper end from 1 to positive infinity. Now notice I didn't put any interval notation in. We know we never include our infinity, so that's going to be a curve. Over here, negative 3 is a value of 0. It can be included. Negative 1 is a place where the function is undefined. It is never included. Positive 1 is a place where the function is undefined. It is never included. So that's my solution to that inequality. Why are these two undefined? Well, because they come from the denominator. They would cause me to have a 0 in the denominator. Why is this a function value of 0? Because it comes from the numerator. 0 over anything is equal to 0. Okay, now what if we're thinking about the same, very same inequality setup, except I've changed my inequality symbol. So now I've got less than 0. So now I'm interested in the negatives, the values where my graph would be below the x-axis. And it does not include function values of 0 because it's not or equal to. So what does that change? Well, now I'm interested in my negatives, so I'm interested in these two intervals. And since I'm not including any function values of 0, I'm not going to have any square brackets, even here at this negative 3. So my intervals here, I've got this left interval, negative infinity to negative 3, or this middle interval between negative 1 and 1. Okay, let's do a couple more examples, and then we'll be done with this section. Find the intervals that satisfy the following inequality. So we've got greater than or equal to, oh look at that, both of these are greater than or equal to. That's fine. That means we're looking for the positives for both of them, and we can include function values of 0. Think about our steps. First step is to set it to 0 on one side, a single ratio in lowest terms on the other. So we need to do a little bit of math here. I'm going to need to subtract 1 to move that over and set it to 0. So now I've got 2x over x plus 1 minus 1. And since this is a fraction, I'm going to go ahead and write my 1 as a fraction. Greater than or equal to 0. I'm setting it to 0. But I have to combine these as a single rational expression, which means I need a common denominator. Now, to get my common denominator, I need to create a single denominator that they both share. This denominator is just 1, so I'm going to use this denominator. When I multiply it in over here, I can't just change the bottom. I have to change the whole thing. Anything over itself is 1, so I'm multiplying times x plus 1 over x plus 1. Well, I can now write it over a single denominator because they have that in common. My denominator is x plus 1. My numerator here is 2x, and then I have minus x, 1 times x is x, so minus x, and then minus 1. And I need to clean up that numerator. 2x minus x is x, so I have x minus 1 over x plus 1 greater than or equal to 0. That's the inequality, the rational inequality that I'm looking at. Alright, I'm going to need a number line. How many boundary points go on my number line? Well, I include zeros from the numerator and zeros from the denominator. Zeros from the numerator give me a function value of 0. Zeros from my denominator give me a place where my function is undefined. So I see the two numbers that need to go on my number line are -1 and +1. I've got two boundary points, 3 intervals. This x equals 1 comes from my numerator, so that's a function value of 0. X equals -1 comes from my denominator, so that's a place where my function is undefined. I need to check a point in each interval. 0's in here, that's super easy to check. I'm going to do 10 and -10 as my large values. I can pick kind of whatever I want. I could do -2 and +2 if I wanted to. It doesn't matter. Now, I'm not working with this that I was presented with originally. I'm working with it set to 0 because that's how I can compare it to our number line that represents the x-axis. Alright, I've got 3 points to test. I need to test -10, I need to test 0, and I need to test +10 and see if I get positive or negative values. -10 minus 1 is -11. -10 plus 9 is, or plus 1 is -9, and a negative over a negative is a positive. So this interval, everything over here is positive. In this middle interval, if x were 0, 0 minus 1, 0 plus 1, that's a negative value, so everything in this interval is negative. And then finally, if I do a positive 10, 10 minus 1 is 9, 10 plus 1 is 11, that's positive. So that interval is positive. My solution I'm interested in are values where x, my function is greater than or equal to 0. That's these two end intervals. So from -infinity to -1, or +1 to +infinity. This is undefined, never included. This is a 0, so I get to include that +1. Okay, I want to challenge you to pause the video. Try working through your process with this inequality, and then restart to see if the things that I do are the same things that you did. Remember that I'm not able to pause mine and then pick it back up, so I'm just hanging out. You need to pause, do your work. We're going to set it equal to 0 first. Multiply in a common denominator by multiplying by the denominator over itself, that well-chosen 1. Now they have the same denominator, so I can write it as a single rational expression. X plus 4, -3 times 2x is minus 6x. -3 times a -1 is positive 3. Clean that up. X minus 6x is a -5x. 4 and 3 is 7. This is the one I'm working with. I'm not going to work with that one. I'm going to work with this one. I've only got one expression in the numerator, one expression in the denominator, so that means I'm going to have, again, just 2 boundary points on my number line. From my numerator, if I set that equal to 0, from my numerator, got a positive 7/5. From my denominator, 2x minus 1 equals 0, positive 1/2. So both of these values are positive. I want to make sure I do them in order from least to greatest. 1/2 is less than 7/5. 7/5 is a little bit more than a positive 1. That would be 1 2/5. 7/5 came from my numerator, so it's a function value of 0. 1/2 came from my denominator, so it is a place where my function is undefined. We're going to go in and pick test point values. I can pick 0 over here. I can pick 1 there between 1/2 and 1 2/5, and then I can pick whatever I want to here. So I can pick, I'm going to pick 5. Alright, I need to check those test points. So if x equals 0, if x equals 1, if x equals 5, and I'm plugging it into this polynomial inequality that I'm working with over here. So if x is 0, anything times 0 is 0, that leaves me with 7 over negative 1, which is negative. If x is 1, that's negative 5 plus 7 over 2 minus 1. That's 2 over 1, that's positive. That's what I care about, not the value as much as the sign, positive or negative. If x is 5, that's a negative 25 plus 7 over 10 minus 1. Well, that's going to be a negative numerator and a positive denominator, so that entire interval is negative. And which intervals am I interested in? I'm interested in where my function value is greater than or equal to 0. So that's that positive interval that I want between 1/2 and 7/5. It's or equal to, so I can include the values that are zeros, but I never include the values where my function is undefined. So I'm only interested in that one interval on the domain.